before I start, I got a demo for you guys in the end. I built a CNN TensorFlow that can classify different types of road signs. So I'll kind of show you guys that in action in the end, and hopefully you like it. But right now, let's talk numbers. Each year, $1.3 trillion is wasted due to a combination of cost for car crashes and time and gas wasted in traffic. This is a huge problem. This $1.3 trillion, guys. It's not just money we're wasting, it's lives that are being affected too. Just to put this in perspective, let's compare this with World War I. In the course of 4 years in World War I, 37.5 million people were both killed and injured. Now, each year in car crashes, we have 51.2 million people who are actually both killed and injured. Yeah, this is crazy. This is actually crazy. But all these lives, money, time, and gas wasted can all be drawn to one root cause, and that is the human driver. The human driver makes too many decisions based on his emotions, right? He wants to show off to his friends. He wants to be driving a nice Lambo and wasting gas. He doesn't care. He doesn't care about the environment. He wants to show off to his friends, right? But you know who doesn't want to show off to their friends? Self-driving cars. Self-driving cars, they have one purpose. That is to go from point A to point B the most safest and efficient way possible. And that's exactly what they do. Now, self-driving cars are actually really cool if you look at the engineering, the math, the computer science, and how it comes together to actually make a car that drives by itself. So let's kind of dive into the hardware. So there's three main components to the hardware of a self-driving car. Let's talk about radar. Radar stands for radio detection and ranging. So it's composed of a transmitter and a receiver. The transmitter transmits radio waves, and the receiver would measure the time that it takes for a radio wave to leave the transmitter and come back to the receiver. And by doing this, it can actually detect objects, how far they are around the car. And by using other factors, it can also do this by using other factors like how fast the car is going too. So if you have stuff like blind spot detection, like forward collision warning in your car, that's all radar. That's all radar. Another part of this is LiDAR. So LiDAR is basically the same concept as radar, except it uses laser pulses instead. And unlike radar, LiDAR is constantly moving on the top of the car. As you can see here, it's like on the top, it's always moving. So it's constantly emitting laser beams, millions per second. And by doing this, it can create like a 3D map of the car's surroundings, which really helps the self-driving car understand its environment in more detail. But these sensors, they're cool and all, right? But for the car to actually see and understand its environment thoroughly, we need to have cameras. So cameras allow the car to see like people and like allow it to stay in the lane line, see buildings and stuff. But you can't just expect to slap cameras on a car and like expect it to understand everything. We need computer vision. Now computer vision allows a computer to see and understand an image or video. Now this is a huge application in self-driving cars, right? We use so many types of computer vision algorithms in self-driving cars. So an example of one of these computer vision algorithms is image classification. So image classification would take an image and it would tell you what this image is. So for example, here's an image of a car, a really nice car. It would take the image in and just be like, that's a car. We can go a level deeper. We can look at object detection. Now object detection would tell you where the object is in the image. So for example, it'll take a car as an input, right? The image classification algorithm will tell you it's a car, and the object detection algorithm will tell you, oh, the car is in the center, and it could represent that by like a bounding box, and drawing a bounding box in the center. Now the third one is depth perception. Now this algorithm is more of like includes a lot of hardware too. It operates the same way our eyes see depth. So what we have is we have two cameras which are looking at the same object from different angles, and we would take the difference of the object in camera 1 and the difference of the position of the object in camera 2, and by doing that we can kind of get a good idea of the depth of this object. The last example I'll give, there's a lot more, but here's kind of the main ones, is point cloud deep learning. Now, I talked about LiDAR before, so point clouds is the type of data that LiDAR would output. Now, we can do deep learning on this. An example of that would be called semantic segmentation. Now, semantic segmentation is a more intense and granular form of doing object detection. So instead of drawing bounding boxes around objects, you'd actually classify each pixel in the image to its respective class. So for example, here there's a lot of stuff in this image. We can look at chairs, right? Instead of just drawing a bounding box around a chair, it would actually like represent the chairs by like a red pixel, which is like a lot more accurate. And obviously in self-driving cars, we want the most accurate classification possible. But computer vision isn't perfect, right? There's many problems. The biggest problem being that we don't fully understand our brain. Now, a lot of computer vision, artificial intelligence, and machine learning is based on how the human brain works. So an example of this would be like we know how like our brain can like identify stuff like like maybe stuff that we see, like a tree, or like a river, but we don't know how our brain like analyzes these things in detail, like provide, would take what this this river would symbolize, a tree would symbolize, right? So for example, like there's a beautiful picture of our parliament here. A computer vision algorithm could tell us, oh look, there's a building and a tree and river, but it can't tell you like the colors of this image would like go together to create like a soothing effect for the viewer, right? It can't read emotions. So that's our biggest problem, which is one of the biggest roadblocks to some of the future in computer vision. So a future in computer vision, this could be like pairing a computer vision algorithm which can recognize emotions, and maybe we could pair that with like a natural language generation algorithm, which would like the computer vision algorithm will like talk about what it analyzed from the image. Like that's kind of a future, and that is then a building block to creating an artificial general intelligence. That's a vision from Marvel. I don't know if you guys watch Marvel, you probably do. But he's more of like an artificial super intelligence. He's God. But anyways, vision is a big part of how us humans are intelligent, right? So right now, if we want to be able to build some artificial general intelligence, we have to create computer vision algorithms that are on par with our level of understanding and our level of vision. That's kind of a brief introduction to computer vision. Let's talk a bit more about CNNs, which is my project. So CNNs, like I mentioned before, they are image classification algorithms. So they would just take an image as an input and they tell you what this image is. So there's two parts to this. There's feature extraction and image classification. Now feature extraction would look at an image and extract features like edges, shapes, and colors, and it would pass these features on to the image classification section. Now the image classification section would look at these features and it would try and correspond these features with one of the predefined outputs. So let's say your network is looking for cats and dogs, right? So then the image classification part would try and correspond these features with either a cat or a dog, and then the network would output what it thinks the features are, and it would compare it with what the programmer said this image is, and it would calculate how off it is or how wrong it is, and then it would update its weights so that next time it can classify it better. That was a really high-level example, right? Let's take a look at each of the layers in depth. Now, firstly, in form propagation, we first encounter a convolutional layer. Now, we'll start off with an image matrix and a kernel. Now, remember, an image to a computer isn't like a nice bunch of colors, right? It's values. It's an array of pixel values that would represent how how dark the pixel is. So where 100 would be really dark and light would be really white. So a higher value pixel would be like more dark and a lower value pixel would be lighter. Now we have our kernel here. Now that bad boy, he's the guy who learns all the features, right? So what we're going to do is we're going to pass this kernel over our image. And then we're going to perform element-wise multiplication, meaning that we're going to multiply each value in the kernel by each value in this section of the image. So here's kind of what it would look like. So as you can see, we're going to multiply the top left value in the kernel by the top left value of the image for this iteration. And we're going to do all the values, and then we're going to sum up all those values, and that will be our first feature. Now we're going to do that for all the pixels in the image, and I'm just going to keep on going. And here is our feature matrix. Now these are the features that this kernel would have extracted from the image. But you're like, okay, like I kind of get the multiplication and everything, but like how does this actually extract features? Well, since this is kind of an example of the first time we would pass an image into the network, let's take a look at an example of a kernel matrix that has been performed multiple iterations on, so we can get a bit more clear idea how this works. So here's an image of an X, right? What do we notice right away? Well, there's two diagonal lines, and both these diagonal lines are perpendicular with each other. So we want some feature matrix that can actually tell us if an image would contain diagonal lines. So we're going to use something called the diagonal feature. Now, this diagonal feature will correspond with sections in the image that have diagonal lines. So here in the top left corner, as you can see, the diagonal feature is pretty similar to this section of the image, right? Same with basically all the corners of the image and the center, which I forgot to animate. And as you can see, our feature matrix resembles an X, right? Coincidence? I think not. And here's my code. I don't really want to go through it because I got a lot of slides to go through. But it's basically just, it goes to the image, and it would perform this element-wise multiplication, and then it would return a new feature matrix, right? So yeah. And after we have done our convolutions, we would pass it through our ReLU activation function. Now what this does is it would take all those negative values out, and because, think of it, if a feature is negative, that means this part of the image really does not correspond with what we're looking for. So if we're looking for edges, it's saying that this one would say the top right of this image would there's no edges. So that means we don't really care about that section. So just to speed up computation, speed up training time, let's get rid of all those. So this is what the ReLU activation function does, and here's my code for it. Basically just pick on it, does exactly what I explained. And after we go through our pooling layer, our ReLU activation function, we're going to go into our pooling layers. Now what our pooling layers does is it's similar to convolution, except we don't do any multiplication. We're just going to extract the biggest value from each section of the image. So, and what does the biggest value mean? That means the most important feature of this section of the image. So we're just going to do that for all the sections. Like it's kind of the same idea as convoluting. Like we're looking at each different section of the image, and we're just extracting the biggest feature. Here's my code. It's basically does exactly what I said. It's going to look at each section of the image and it's just going to extract the biggest feature. And yeah, and there you go, guys. That is feature extraction. And here's everything combined in TensorFlow. The code you saw before was in NumPy. And this is basically multiple layers of convolution, ReLU, and pooling. We're going to do that many times because we want to extract more intense features each time. So this one is going to, the first time we do that, it's going to extract like general features. And then the second time we do that, it's going to extract features from those features, and just going to keep on doing that because we want to have the most accurate classification possible, right? So yeah, and now we're going to image classification. Now we have we're going to take once our feature extraction is finished, we're going to take the final output from the last pooling layer, and we're going to pass it into our feature classification network, which is just a general neural network, okay? And what we're going to do is we're going to take all the rows in that feature matrix, and we're just going to horizontally stack them, because our neural network only takes a one-dimensional input. That means it can't take a matrix, which is an n by n dimensional matrix. So we're going to pass it into our neural network. It's going to do its thing, weights times inputs, plus a bias, an activation function, the ReLU activation function we'll use. It's going to do that for some hidden layers, so in this case, 2 hidden layers. And then right before our outputs, we're going to apply the softmax activation function. And this softmax does is it essentially takes our inputs and it's going to scale them to between 0 and 1. And it's going to take and make sure all of our outputs of the network would correspond with a probability that this feature matrix would be a certain class. So I actually was going to have a slide detailing this, but I deleted it for time reasons. So yeah. And that was basically all of for propagation, right? So we're going to have our feature extraction part, which extracts the features of the image, and then we're going to have our image classification part, which is going to classify the features based on our predefined classes. But that was one part. That's only the beginning of the convolutional neural network, right? We never talked about how the neural network actually learns, which is what most people kind of skip. But we're not skipping that. We're going to take a dive into backpropagation, guys, okay? So how we do this is an algorithm called steepest descent. So our goal from steepest descent is to minimize the error function. Now, how are we going to do this? We're going to see how the weights matrix would affect our error function, and we're going to try and minimize our error function by tweaking our values in the weights matrix. Another way to say this is taking the partial derivative of the error function to the weights matrix. Now you're like, okay, hold up, what is a derivative? Now, I'm pretty sure you guys all passed grade 9 math, right? Taking the slope of a line. But have you ever thought of taking the slope of a curved line? I don't think so. Well, you can't really do that actually. But what you can do is you can take 2 points on this slope, bring them like super close to each other. It's almost like they become 1 point. And what we're going to do is we're going to draw a line that is tangent or equal to the slope at these 2 points. I'm going to calculate the slope of that line. And we're just going to keep on doing that, right? Over and over until we get to the minimum value of our function. But the derivative, it returns the fastest way to maximize our function. So what we're going to do is we're going to calculate the negative derivative, or you may have heard the negative gradient. Now here is an example of backpropagation from our output layer to our last hidden layer, okay? Now I told you before, we're going to calculate the partial derivative of the error function to the weights matrix. But to calculate a derivative, the independent variable, in this case the weights matrix, has to be directly related to our error function, but in this case, clearly it's not. You can see the error function is related to the output function, which is related to the input function, which is then related to the weights matrix. So we're going to have to use something called the chain rule. Oh, I forgot. Yeah, the chain rule here. So we're just going to take partial derivatives. We're gonna check how the weights matrix would affect the input function, and then we're gonna see how the input function affects the output function, and then we're gonna see how the output function affects our error matrix, and then we're gonna update our weights based on all these derivatives that we calculated. I forgot about that. And we're just going to do this for each layer in the neural network, right? So the one I showed you previously, this weights matrix only affects error function 1. But if we go to the next layer, these weight matrices both affect both error function 1 and error function 2. So we're going to have to take the partial derivative of the total error function to our weights matrix this time. And it's the same thing, right? Same kind of concept, using the chain rule to find how this weights matrix would affect our error function. And we're just basically going to do that for all the layers, and I don't want to talk about this. It's going to be like an hour. So yeah, and we're going to keep on doing this. This equation only keeps on getting longer and longer. So we don't want to go there. And we're just going to keep on doing this, right? But the only part where we actually start doing different operations is when we get to our convolutional layers. Now we're going to take our weights from our classification layers, and we're going to take our original input, and what we're going to do is we're going to perform the same convolutional operation that we did in the beginning, except this time we're going to try and find the new weights. So we're going to apply our derivative matrix onto our convolutional, onto our image. So as we can see, we're going to do element-wise multiplication with each of the derivatives on each section of the image. And we're just going to keep on doing that, right? Keep on doing it. And then we're going to take the sum for each of the weights, each of our all of our products, and that's going to be our new weights. So all those sums, we're going to add all those up, right? And after the demo, all right? So I just talked a lot, so hopefully you guys can record. Use my little demo. All right, let's load this up. All right, so here, this basically is a convolutional neural network that classifies different traffic signs. It can tell you what a road sign is, right? So someone pick a number between 1 and 12,000. Yeah?
896.
896 it is, okay. We're gonna use the 896 image in this data set. I honestly have no clue what that is. Okay, it's some car sign, okay?
What?
Huh? No plastic, yes, thank you. All right, so we're gonna, let's see if our network is right. Okay, so it predicts it's class 9. Now let's go into my computer files. Let's go to class number 9, and oh, look at that. It's right. It's a really trash image. Look at that. It is right. There we go. So our network is correct, all right? And there you go. That's the presentation.
That was the most enjoyable presentation of derivatives I've seen.
Or maybe his future is like being a PhD in math, man. Seems like
You could literally go on YouTube and be one of those brown guys. I'm watching.